We're all constantly trying to figure out what's going to happen next, right? Whether it's in the stock market, forecasting sales, or even just trying to guess the weather. But have you ever stopped to wonder how we actually do it with data? How do machines learn to see into the future?
It's a massive question, isn't it? But, in the world of data science, the answer isn't some deep philosophical mystery. It's actually surprisingly practical. And it all boils down to one simple but really powerful idea.
And that's it. That's the heart of forecasting. We look backwards to look forwards. The whole idea is that the patterns, the trends, the cycles from the past, they hold the clues for what's coming next. And one of the most powerful tools we have for finding those clues is a statistical model with a slightly intimidating name.
Say hello to ARIMA. Yeah, it stands for AutoRegressive Integrated Moving Average, which is a total mouthful, I know. But please, don't let that name scare you off. At its core, ARIMA is just this brilliant, super structured way of capturing past patterns and data over time so we can make a solid forecast. So, here's our game plan for today. First, we're going to tear that acronym apart and look at its three core pieces. Then we'll tackle a really crucial concept called stationarity. After that, we'll figure out how analysts find the perfect model. And finally, we'll put all the pieces together and watch a forecast come to life. Ready? Let's dive in.
Okay, so first things first, let's pop the hood on ARIMA. Instead of thinking of it as one big, complex thing, just imagine it's made of three simple building blocks. Each one has a very specific job to do.
The first block is AR, for autoregressive. Honestly, this is the part that just makes sense. It's the simple idea that today's value is probably related to yesterday's value. Think about it like the weather. If it was sunny and 75 degrees today, you have a pretty good hunch it's going to be kind of similar tomorrow. That little P you see there, it just tells the model how many days or steps into the past it should look.
Next up, we've got I for integrated. Now this is the secret sauce. See, a lot of data in the real world has a trend, right? Like sales that are slowly climbing month after month. The I part is so clever because it handles this by looking at the change from one point to the next, instead of the actual values. That simple trick gets rid of the trend, it stabilizes the data, and it makes all those hidden patterns way easier to spot. The D just tells us how many times we need to do it.
And the final piece of the puzzle is MA for moving average. Now, this one's a little different. It's not about past values, it's about past mistakes. The model makes a guess, sees how far off it was, and then it uses that error to make a better guess the next time around. It's kind of like a self-correcting thermostat that's constantly learning from its own errors to zero in on the perfect temperature. And that cue, it just tells the model how many past errors it needs to remember. So when you put it all together, these three pieces, AR, I, and MA, come together to form the model's signature, ARIMA PDQ. And the real trick, the art of it all, is finding the right numbers to plug in for P, D, and Q. That's the key to building an amazing forecast. Now, let's zoom in on that I component we just talked about because it's connected to a concept that we absolutely have to understand. It's called stationarity, and it's all about making wild, unpredictable data nice and predictable. Okay, so what on earth does that actually mean? In simple terms, it means the data has a stable average, that's the mean, and its ups and downs, its variance, stay pretty consistent. You can think of it like this. A model like ARIMA needs the rules of the game to stay the same. If the goalposts are always moving, there's no way it can predict the next shot accurately. And here's a perfect picture of what that looks like. On the left, you see data with a clear upward trend. It's totally non-stationary. But then, after we do that differencing process we talked about, look at the result on the right. The trend is just gone. The data is now bouncing around a stable average. This is the kind of data that an ARIMA model can really sink its teeth into. Okay, so we know we need our data to be stationary, and we know we need to pick those magical P and Q values. But how? It's not just a random guess. There's actually a systematic process for this, and it's called the Box-Jenkins method. This method is really just a three-step loop you keep repeating. First, you identify a possible model by just looking at your data. Second, you estimate the model's parameters. And third, you do some diagnostic checks. You basically look at the model's errors, or what analysts call residuals, to see if it's any good. If it's not working, no problem. You just loop right back to step one and try a different combination. So how do we actually do that first step, the identification? Well, this is where visualizing your data becomes a total superpower. Analysts use two very specific charts.
the autocorrelation function plot, or ACF for short, and the partial autocorrelation function plot, the PACF.
I want you to think of this table as a secret decoder ring for those charts. The shapes and patterns you see in the ACF and PACF give you really strong clues about what your P and Q values should be. For example, if you're looking at a PACF plot and the bars just suddenly drop to 0 after, say, 2 steps, that's a massive hint that you probably need an AR model where P is equal to 2.
Let's look at a real one. This is an ACF plot. See how the bars get smaller and smaller, kind of gently tailing off towards 0? That slow, decaying pattern is a classic signature. And if we look back at our decoder ring, that pattern points us directly to an autoregressive, or AR, process. Pretty cool, right?
Okay, we've done the hard work. We've identified our P, D, and Q. We've run our diagnostic checks, and now it's time for the payoff, turning this model into a real, actual forecast. The process from here is actually pretty straightforward. The machine takes the model we chose, say an ARIMA 111, and we feed it all of our historical data. It crunches all the numbers, analyzes the past patterns, and basically trains itself. Once that training is done, the model is ready to go. It can project those patterns forward and predict values it has never, ever seen before. Now, a lot of the time, analysts won't just build one model. They might try a few different combinations of P and Q. So how do they decide which one is the best? Well, they use scoring metrics, like something called the AIC, and the rule here is super simple. The model with the lowest score wins. It's all about finding that perfect balance between accuracy and simplicity, and the AIC helps find that sweet spot. And here it is, the final product. You see, the model doesn't just spit out a single line of future guesses. It also gives us these prediction intervals, that shaded area you see around the forecast. And this is so important because it gives us a range of what could plausibly happen. It tells us how much uncertainty there is in our prediction.
When it comes right down to it, ARIMA isn't just one model. It's a whole way of thinking about time. It's really a foundational concept that's been built upon over the years. It's been extended to handle things like seasonality with SARIMA, or even adapted for data with long memory using something called ARIMA. That incredible versatility is what makes it so enduringly powerful.
And all of this brings us to one last thought. We've seen how these models can systematically break down the past to predict the future with this remarkable logical structure. And it kind of leaves us with a fascinating question, doesn't it? In a world filled with these powerful algorithms, what's the role for our own human experience and our own intuition? Definitely something to think about.